Welcome back to The Explainer. Okay, let's dive into this, because today we're tracing the dramatic rise, the spectacular fall, and the honestly really unexpected rebirth of literally the most famous buzzword in modern physics, string theory. For decades, it was championed as the ultimate key to understanding our universe. But then, it kind of became a punchline for empty scientific promises. But as we're going to see today by breaking down some major recent developments in the physics community, the story is far from over. It's actually just evolving into something completely different. So is string theory dead? It's the question that has absolutely divided physics departments all around the world. Did it fundamentally fail its original, incredibly grandiose promise to explain, well, everything? The short answer for a lot of folks is a resounding yes. The tension surrounding the current status of this whole framework is super palpable right now. You've got brilliant minds who dedicated their entire lives and careers to it, and then you have equally brilliant minds who view the whole thing as a decades-long detour that basically led theoretical physics straight into a dead end. And that academic clash, it's perfectly encapsulated by Peter Woit, a mathematician over at Columbia University. He represents a fierce, hardened line of criticism against string theory. He argues that the framework has just become so vague, so completely untestable, and blindly adopted with this almost tribal allegiance by its followers. Listen to this. He calls it just not science, and a really insane situation. Wow. When top academics are calling a mainstream theoretical framework not science, you know for sure we are dealing with a deeply polarized landscape. Which brings us to Chapter 1, the theory of everything. Now, to really understand this intense backlash and the surprising new pivot happening right now, we have to look at the boom phase. We got to go back to the origins to understand the sheer immense ambition behind string theory. It actually started out as a highly elegant solution to the deepest problem in physics, reconciling the rules of the very small, quantum mechanics, with the rules of the very heavy, gravity. Let's look at how this unfolded. Back in the 1960s, Italian physicist Gabriele Vinciano was looking at particle collider data. Relying purely on basic principles about nature, he discovered a mathematical formula that perfectly seemed to capture the behavior of elementary particles. Well, soon after, other researchers looked at his math and realized, wait a minute, this isn't describing standard point-like particles at all. The equations were actually describing the behavior of tiny vibrating strings. And over the following decades, this quirky mathematical discovery blossomed into a massive, wildly ambitious framework. So what exactly is it? At its core, string theory is a framework suggesting that all the fundamental particles and forces in the universe aren't made of tiny little dots, but they arise from tiny, one-dimensional vibrating strings. Think of it kind of like a cosmic guitar. Just as different notes and chords emerge from guitar strings being plucked at different tensions and frequencies, all the different particles in our universe, quarks, electrons, photons, they're basically just different notes being played by these fundamental vibrating strings. And this brilliantly illustrates why physicists fell in love with the idea in the first place. See, when you use traditional point particles, which are just these infinitesimal dots with zero size, the math goes completely crazy when you try to cram quantum mechanics and gravity together. You get all these wild infinities that just break the equations. But because strings are extended objects, they literally spread out the interaction. They beautifully sidestep those mathematical headaches that had plagued physicists for decades. Honestly, it was a total revelation. You can really feel that intoxicating original dream of the theory in this quote from theoretical physicist Renate Lal. The ultimate hope was that researchers would discover one single, elegant, magic formula, a true theory of everything. The idea was that, from that one master equation describing these vibrating strings, the absolute entirety of the universe, from the Big Bang to black holes, right down to the atoms in your body, would naturally unfold. It was the ultimate prize in theoretical physics. But all of this massive ambition leads us straight into Chapter 2, a mathematical headache. Now, what's really interesting about this slide is how this beautiful, elegant dream turned into the controversial, highly criticized mathematical headache it's often viewed as today. As researchers dug deeper and deeper into the math of string theory, things got incredibly complex. Just look at this number, 10. For the mathematics of string theory to function properly and remain consistent, our universe cannot just have the 3 dimensions of space and 1 dimension of time that we experience every day. No, the math strictly requires at least 10 dimensions. That means our 4 familiar dimensions plus 6 additional dimensions of space that are curled up so tightly and are so infinitesimally small that they are completely beyond our human perception or any of our instruments. And it gets worse, because the requirements only got more demanding from there.
The theory became incredibly baroque. It required new theoretical symmetries in nature that our actual particle colliders simply haven't found. It didn't just describe our universe either. The math allowed for an unimaginably vast landscape of possible universes, a multiverse, which made it incredibly hard to predict anything specific about ours. And perhaps the most fatal flaw of all, the strings themselves are theorized to be so incredibly tiny that we could literally never build a collider big enough to probe them directly. So it basically became functionally impossible to test. And that is exactly what caused so many critics to just lose hope.
Which brings us right to the modern plot twist of our explainer. Chapter 3, Back to the Basics. So, after decades of essentially a stalemate, a major new movement is happening right now in physics. Researchers like Clifford Chung at Caltech and Henrietta Elvang at the University of Michigan aren't abandoning string theory, but they are radically changing how they approach it. They're utilizing this revived methodology called the bootstrap philosophy. And here's how it works. Instead of starting with some insanely complex 10-dimensional string framework, they build from the ground up. Step 1. Start with very conservative minimal assumptions. Things we know are true, like all probabilities must add up to 100%, and the laws of physics must remain consistent for moving observers. Step 2. Add a specific theoretical constraint to the mix. Step 3. Crunch the numbers. And astonishingly, when they do this, they find that the only mathematical framework that survives these basic principles inevitably looks exactly like string theory. To give you an idea of what those specific constraints in Step 2 actually look like, let's focus on one invoked by Clifford Chung's team, ultrasoftness. It's basically this unproven idea that the probability of certain particles interacting drops off at a very specific rate at super high energies. Now, another team led by Henrietta Elvang used a totally different constraint called supersymmetry. But here is what's so fascinating. Regardless of which specific theoretical constraint they applied to their basic assumptions, the math led them right back to string theory. It's like all roads lead to Rome. Of course, the critics are absolutely not convinced by this new bottom-up approach. Remember Peter Voigt? Well, he pushes back hard against this bootstrapping method. He makes the point that there is zero experimental evidence to justify adding these special constraints like ultrasoftness or supersymmetry in the first place. He argues it's literally just circular reasoning, saying you're just injecting assumptions into the math that are specifically designed to spit string theory back out at the end. So yeah, those accusations of tribal allegiance, still very much alive and well. But Clifford Chung has a really pragmatic defense against this. So the crucial point is, as he puts it, I don't have a dog in the fight, I just work here. I love that. Chung doesn't even identify as a string theorist. He openly admits that string theory completely failed its original promise to deliver the theory of our world. His goal with this new methodology isn't to prove string theory is the ultimate reality. Not at all. It's just to explore what mathematical theories are even possible when you apply really rigid rules. And this fundamental shift in perspective leads us to Chapter 4, Building a Toy Universe. We are basically witnessing a total redefinition of string theory right now. It's no longer treated like the sacred text, it's a sandbox. Henrietta Elvang perfectly outlines this contrast for us. On one side, we have the real world. It is complex, it is incredibly messy, and as critic Renata Lal points out, it requires strict reality checks in physical experiments to make sure we aren't just getting completely lost in the math. But on the flip side, string theory serves as this incredible toy model. It gives physicists a perfectly controlled sandbox where they can build complex mathematical tools, test out constraints, and maintain total control over all the variables, even if it doesn't directly map onto our specific, messy universe. Let's move to and see how this builds a path for the future of physics. We've got a lot of different perspectives here. Andrew Tolley over Imperial College London suggests this new bootstrapping approach could actually inspire real experimental tests, essentially tying the low-energy physics we can measure to the high-energy physics we currently can't. Meanwhile, Renate Lal offers a very healthy warning, reminding the field not to think outside the box for so long that they just abandon experimental reality altogether. But Clifford Chung offers perhaps the most exciting takeaway of all. By building up from the bottom, we now know exactly what rigid rules govern these models. Meaning, if we want to find a totally new alternative to string theory, we now finally have the map to do it. So by stripping away the grand promises of a theory of everything, physicists have actually found something arguably much more useful, a highly advanced mathematical testing ground. String theory might not be the final answer, but it's helping researchers figure out exactly what the right questions are. Which leaves us with this incredible thought to ponder. As researchers continue to explore the strict rules of this toy universe, what if the ultimate alternative to string theory, the true laws of our cosmos, ends up being discovered using the very tools forged inside it?